All right, good afternoon, students. I apologize for the late start, but just some circumstances beyond my control. All right, so today we start a new topic, network analysis. We should be able to complete this today, and then based on when we do that, we will jump straight into filters. All right, so network analysis. Many of you would have done this if you have already done instrumentation and control systems, then you would have completed a lot of what we'll be discussing this afternoon. We'll be approaching it, however, from a circuit analysis standpoint. So some of the things will be familiar, but some may be a little different. But ultimately, we'll get to the same place. At least I hope so. All right. So let us start by talking about some basic principles that we would have already been introduced to, but I will nonetheless go it over for your benefit. All right. So we start by looking back at Laplace. What do I mean by Laplace? And you have looked at Laplace in mathematics. You have looked at Fourier analysis. We have used a little Fourier analysis, a little of it, but at least you having done it in math makes our use of it, I hope, a little easier. And of course, Laplace and Fourier are connected. Yes, Laplace around the real, and the Fourier analysis about the imaginary portion of a complex number. So that's basically what it's all about. But more importantly, and what we're more interested in, is that Laplace transforms are really a tool similar to us using logs. We want to multiply two numbers, we add the logs. We want to divide them, we subtract the logs, that sort of thing. But having done that, to get back to the final answer, of course, we'll find the antilog. In the same way, we will use Laplace, which is simply transferring our circuit elements from the time domain to the frequency domain, do the analysis in the frequency domain, and then find the inverse Laplace in order to determine what the actual signal is. So, the long and short is that Laplace transforms is just a tool, right? You have already looked at it in math, as I said before. We're not going to be delving into a lot of that, but we'll just see how we would use it in our circuit analysis. So as a function, the Laplace is given by Laplace of a function f of t is given by the integral from 0 to infinity of f of t e to the minus st with respect to t. Okay. So that is how we define a Laplace transform mathematically. Okay. So in moving from the time to the frequency domain, and just to distinguish, we would move, we write in the frequency domain in capitals. That's how we distinguish from the time and the frequency. All right. Now, before we can talk about analyzing a circuit in the frequency domain, what we want to first do is to define the various elements that we are accustomed to, define them in that frequency domain. All right. So we find the Laplace for your resistor, your inductor, your capacitor. right? So that's where we're going to start. So we want to define them in that frequency domain, and then look at how we do the analysis, and then of course come back to the time domain. Well, to be honest, most of our work here will be left in the frequency domain, but you, having gone through Laplace transforms, would have been able to find the inverse Laplace, the inverse transforms, and just be able to see the results in terms of the time domain, which is what we're accustomed to. Okay. So for a resistor, from Ohm's law, we know V equal IR. And since the resistance would not change, then the Laplace of the voltage, which is the Laplace of I, since R is a constant, yes, we therefore get, so from lowercase v being equal to I, which of course we know is the instantaneous I, which is in the time domain, times R being constant, we therefore have V being equal to IR. Okay. So uppercase I, Laplace of lowercase I, and V, of course, Laplace of instantaneous voltage V. So excuse me a sec, please. Let me see what is happening outside. For your resistor, therefore, in moving from the time domain, which we have on the left, to your frequency domain, yes, the resistor will be the same. The only difference, of course, is with your instantaneous current and voltage, and your instantaneous current, your current and voltage in the frequency domain. So, in terms of your resistance, it's the same in both the time and frequency domains. So when we are converting our circuit or transitioning our circuit from time to frequency, the resistor remains the same. That's what we're really saying here. With respect to your inductor, we know that our inductor, if we assume an initial current of I0, and we all know the principles regarding the operation of our inductor. Yeah? So with an initial current I0, the equation for the voltage across the inductor, we know would be equal to L di dt. Yes? And going back to the definition that we had of Laplace, which is the integral from 0 to infinity of f of t with respect to t. Yep. If you were to do that for this function, f of t e to the minus st, of course. For to do that for this function, then v would be equal to L into Si minus I at 0 minus. And of course, I at 0 minus, we know is equal to I0. Yes, Mr. Morgan?
I missed something on the previous slide. I just wanted to skip back for a second.
All right, you can get that in the record. Let's just move on. I'll repeat, it will be repeated later. All right? Let's catch that on the record again. So for V, we have L times Si minus I0 minus, and I at 0 minus, we know would have been the initial current. So expanding, we have SLI minus I0. Of course, if you have a voltage being equal to a component here minus another component, then of course both of these would represent voltages. So graphically, if we want to find the current, yes, we divide through by SL, or we have V plus Li0, and then we divide through by SL to give us I to be equal to V over SL plus I0 over S. Now, in the same way where each of these would represent a voltage, obviously each of these would represent a current. And for us to be adding two currents, it means that we would have a parallel connection. So for two currents to be added, it means that we have two parallel branches. So if I represent this diagrammatically, then the current that we're talking about here would be equal to the currents in two branches. All right, so this would be the voltage representation, and this would be the current representation. So I can represent my inductor in terms of two voltages. And if I have two voltages, it means that it's a series connection. Two currents means that I have parallel connection. Yes? But the key here, students, the key that we're looking at is that in either case, whether I'm representing it as a current or a voltage, in both instances, the inductor in the frequency domain is represented by SL. That's the key that we want to focus on. So for the resistive, for resistor, it's represented the same way in both the frequency and the time domain. Yes? And for the inductor, we have in the frequency domain, did I restart? In the frequency domain, or sorry, in the time domain, it's L. Yeah. In the frequency domain, it's SL. All right, do we have this? Okay. For your capacitor with an initial voltage V, yes. Again, the current will be given by C dV dt. If we were to take the Laplace, again defined, yes, as the integral from 0 to infinity of f of t e to the minus st dt. Yes, if we did that, then that's the current expression. So we'll get I to be equal to C into SV minus V at 0 minus, or in other words, the initial voltage. Yes. If we were to rearrange this equation for V, So again, this will give us a parallel. This will give us a series connection. Do we have this?
No, sir, it's the right thing. That's for
Okay. All right, so for V, with my series connection, I have V equal 1 over SC plus V0 over S. So this source, that's your V0 over S, yes? But as we did with the inductor, we see that whether we are looking at it as a series representation of two voltages or parallel representation of two currents, what is true in both instances is that the capacitor in the frequency domain is represented as 1 over SC. So in summary, for your resistor, that is represented in the same way, whether in the frequency or time domain. Yep. For your resistor, it's the same whether we are in the time or frequency domain. For your inductor, in the time domain, it's L. In the frequency domain, it's SL. For your capacitor, in the time, it is C. And in the frequency domain, it is 1 over SC. All right. Now, based on what we have in these two figures, if the initial current for your inductor is 0, yes, then it means that this will be 0, and we're left with SL. Similarly, if I0 is 0, then that is 0, and I am again left with SL. All right? For the capacitor, if the initial voltage is 0, I'm left with 1 over SC. Similarly, if the initial voltage is 0, I'm left with 1 over SC. All right? Which is what we're saying here. Yes, Mr. Morgan?
Yes, sir.
Your hand is up. All righty then. So, how does this help us? All right, now, if we have no initial energy, I mean, we have just established that, you know, there was no initial current, etc., no initial voltage, yes? Then the terminal voltage and the current is going to be given by V equals Zi. All right? Where Z is the impedance in the S domain or the frequency domain, yes? And of course, V and I, you know, we're operating in the frequency domain. So if this is true, given that this is true, if those initial conditions are not considered, yes, then what we're saying is that the rules governing circuits in the time domain are applicable in the frequency domain. What does this really mean? Okay? Why do we need to state this?
Sir, that would mean that what we learned up until this point is still applicable even though we're operating in the frequency domain.
Absolutely. Absolutely. Thank you, Ms. Campbell. As Ms. Campbell just said, it means that all the principles that you have looked at, nodal analysis, mesh analysis, you name it, Kirchhoff's current law, voltage law, star delta transforms are all applicable in the same way in the frequency as they were in the time domain. So when you convert and you have the inductor, even though you are now representing it as SL in the frequency and the capacitor as 1 over SC, if you had a connection where you needed to convert from star to delta, no problem, go ahead. All right? The only difference is that L is now SL and C is 1 over SC. So with that said, we have completed most of the theory in terms of, well, in terms of Laplace. That's all we want to say right now. We want to look now at the other aspect of this topic. So we look at the theory of the other aspect of this topic, and then we start applying them. I think I'm going to lose internet in a short while, but we will see. So we have to now define transfer function. And simply put, the transfer function is the ratio of the Laplace of the output to the Laplace of the input. Now, students, output is as how the output is as how we define the output. So in other words, I can have a single circuit, and I decide that the output I'm interested in is the voltage across the inductor. That's the output. The input may be the source, not a problem. But the output can be the voltage across the inductor. It could very well be the current through the circuit, or the, you name it. So output is how we define it. So there's no set point within a circuit or set location in a circuit for which or from which the output is determined. The output is as it is defined. Similarly, the input, right? So the transfer function, H of S, is given by output over input, Laplace of output over the Laplace of the input. So just to expand a little on this transfer function, we have this simple circuit. Derive the expression for the transfer function for this circuit, and the transfer function is defined here as I over VG, VG being the source and I being the circuit current. Can I move on now?
Yes, sir.
So VG is equal to IZ. Now, this is the beauty about working in the frequency domain. In the time domain, a circuit like that, our Z would be based on finding the inductive and the capacitive reactance, etc., etc. We know the drill where that is concerned. Here, Z would be equal to the sum of the individual elements. So I times Z would be R plus SL plus 1 over SC. Yes? So it means that H of S, having simplified, I apologize for any background noises that you're hearing. All right, so H of S is equal to SC or S squared LC plus SRC plus C. Of course, that's just simplifying this expression, which I don't think I really need to stress on. However, one of the things that you'll be asked to produce once you have looked at the transfer function are poles and zeros. All right. And by definition, your pole is the value of S that makes the transfer function infinitely large. So in other words, it is the value of S that makes the denominator 0. So if it's a value of S that makes the denominator 0, in effect, all we're saying is that it's the roots of the equation in the denominator. But the question is, at what point do we determine those roots? And before we speak to that, we also define the zeros. So your zeros represent the values of S that makes the transfer function 0, or in other words, it makes the numerator 0. But again, at what point do we make a determination as to that value of S? Can I move on? Right, silence.
Yes, sir.
So before we determine the poles and zeros, it is necessary to reduce the equation in the denominator to have the coefficient of the highest order S, ordered S, being 1. Of course, the order means here the power to which S is raised. So the highest ordered S, if our denominator has S cubed, S squared, S, and then of course S to the 0, which would be the constant, then the highest order in such an equation would be 3, or which is, for the S cube. So it would make that S cube coefficient 1. If the highest order is squared, then we'll make that particular value of S squared 1. Coefficient of S squared 1. So on and so forth. Once you have done that, then you can find the poles and zeros. Okay, so where do we go from here? So for this equation, we would simplify it. If I'm making the coefficient of S squared 1, then I'll be dividing through by LC. And we'll get H of S equal to S over L, yes, into S squared plus S times RL plus 1 over LC. Quick question, does this equation look familiar? Yes, no, maybe so? Or should I say, does the expression in the denominator look familiar?
Yes, sir.
Yes, sir.
Yes, Mr. Black, where you see that before?
So we're doing complex waves.
When we're doing what?
Complex waves.
Complex waves? No.
Yes, sir.
Complex waves?
No, sir. In
No, sir. No, sir.
resonance
Transients.
and transient.
One.
All right, so you'd have seen this in transients just a couple weeks ago, where we had the RLC circuit, eh? And this would be the auxiliary equation. Yep. All right, and of course, if you found the inverse Laplace of that, then you would get the various options that we had presented for your current expression. Yes, and that is how we then get the A, E, S1, and S2T. Yes, or the A plus B, E, S2 for repeated roots, or the sine beta plus cos beta times e to the minus st. All right, that's where all that this comes in. So if you're comfortable with Laplace, then you can use your Laplace for solving those questions. Okay, so as the point we were trying to highlight is that we are the ones who will define the transfer function. So that expression I just gave you, we were finding a transfer function for I over V. We, however, could have defined the transfer function as the volts across the capacitor. Now I know what the current is equal to. We had already found that, yes? Where we said that V was equal to IZ, so I would be equal to V over Z. Good? So if I know that current, then I can find VC, so because VC is just multiplying 1 over SC by that. And so if this is how we defined our transfer function, then H of S would have been equal to that. All right, so the difference here is just what's in the numerator. Okay? All right. I trust you have this. So this was done with R, L, and C. Yep. What I want to do now is to put some numbers. So I want to derive the transfer function for the circuit and then determine the poles and zeros. And the transfer function here is defined as V0 over VG. So it's V0 over your supply. So based on all that we have said so far, what's the first thing we want to do here?
Redraw the circuit in the
Redraw.
redraw the
Go ahead,
circuit
Mr. Marsh. I didn't hear you clearly.
Redraw the circuit in its frequency domain, sir.
Okay. So I want to redraw the circuit in the frequency domain. And so we have SL, and we have 1 over SC. And our resistances remain the same. Quite frankly, students, the most challenging part of this topic is your ability to do fractions. If you're comfortable with fractions, you have absolutely no problem with what we're doing here. All right. So having redrawn the circuit, any suggestions as to how we go about approaching this?
Yes, sir.
Go ahead.
Nodal analysis.
All right. So based on what we have here, give me the node equations. Call this Z1, call that Z2, and that Z3.
All right, so it would be ZO minus ZG over VO minus VG over Z3 plus VO over Z2 plus VO over 10 to the 6 over S equal everything equal to 0.
All right, so it will be V0 minus VG over Z3,
Yes, sir.
V0 over Z2, and V0 over Z1.
Yes, sir.
Fair enough. So if we apply with nodal analysis, which is in this case, which is the same as applying KCL, yep. Well, V0 minus VG over 1000, V0 over 250 plus 0.05 S plus S V0 over 10 to the 6. And what we are interested in, students, is V0 over VG. So it means that we want V0, we simply need to factorize it from that. So we are going to move VG to the left, or to the right, sorry, and then factorize. We want V0 over VG, so it means that it's all of this to the minus 1. Or I suppose we can take that other route. I mean, it's totally up to you. You could have, just put minus 1 and bring it to the right-hand side, and you have V0 over VG. But, it really doesn't matter. Right? As I said, it's just how efficient you can work with fractions. Can I move on now?
I think so. All right, sir.
Okay. So V0 over VG is 1 plus what we have in the bracket there, all to the minus 1. So I'm simply going to simplify my denominator and then invert. Anybody having an issue with the math? Okay. So we simplify and then we invert. And remember, one of the key things we need to do is to make the coefficient, once we have inverted, then the highest order of S, in this instance, will be S squared. So we want to make that coefficient 1. So it means that in this instance, we'll divide throughout by 5 times 10 to the minus 4. Okay. So H of S, by that, making the coefficient 1, that's the expression we are left with. All right. So given this transfer function, we want to find the poles and zeros. We simply solve for the denominator. Now, listen, I'm putting this in. I'm using the quadratic formula, but obviously, this day and age, you won't waste time with this, eh? You simply just solve that from your calculator and punch in the values. And provide the final value. Which gives us values of P1 and P2 Of course, your zeros or your zero will occur at S equal minus 5,000. All right. So take this question. And any questions so far? Like I said, the principles remain the same. The real challenge is with your manipulation of fractions. And that is where many students have had challenges, but it requires practice. Yes, it requires a bit of practice. Again, I'm not asking you to be using the quadratic equation, the quadratic formula for solving. Obviously, that would become impossible when you get to cubic equations, which we will encounter. So, you just stick it in your calculator and get the results. All right. So take this question from a place. All right, here's the circuit. Note we have defined the transfer function as VR over Vs, which means that this circuit, although it has several more elements than the one before, Vs would still be the voltage across here. Yeah? So it means, therefore, that we could actually use the same approach we did a few minutes ago. Well, let us see. So we would have converted our L to SL. Here's another L, convert that to SL. Convert these to 1 over SC. Okay, so transferring to the frequency domain, as I said, similar approach could be used or can be used. But first, I'm going to take the approach where I'm going to combine these two. All right, so let's go. So this is just product over sum, because those are in parallel. And the reason I'm doing this is just to highlight the fact that, you know, whichever principle, electrical principle you wish to apply, well, as long as you apply it properly, that principle would be acceptable. So that's for the parallel section. Again, just product over sum. And then we have that in series with the inductor. All right, adding that part of the series section. All right. Well, here I'm using voltage divider. Sorry. All right, so because those two sections are in series, we can apply voltage divider. So we're applying voltage divider here. And of course, immediately we have our transfer function, which is VR over Vs, which is how we define the transfer function for this. So I'm now going to substitute the expression we had for Z parallel. Gonna put it back in the equation. Can I do that now? All right, so making that substitution, that's our Z parallel, which we had before. We simplify, and of course, we'll be able to eliminate a couple things there. Oh, sorry. Thought I had everything on the slide. All right, can I move to the next slide?
Well, sir, the principle is simple to understand, but the work out is really nasty. Not gonna lie.
Yes, sir, because I saw it in signals and systems, sir, but not in this dynamics.
All right. So that's just, this is just tightening up the denominator. So of course, these two are common, right? So we can cancel those. All right. And then once we have the fraction, we divide through by the coefficient of s cubed. And that's what we have, divide throughout. And now we can solve for our poles and zeros.
So will the Laplace inverse be needed to?
Pardon me?
Will we be using the Laplace inverse,
Pardon me?
the inverse Laplace of to
As I said at the beginning of the class, that we're not going to be transferring them to the time domain. I did say that at the beginning. But if persons wish to do so, then they can. So from this, we can now find the poles and zeros. And these are your answers. So take the answers for me. It's now 227. I'm going to ask you to use nodal analysis. So I'm going to end the class at this point. Just write down these answers because you want to make sure that you're getting the same results.
Sorry, is it two poles that are one at one or one's equal to two?
Pardon me?
I see you have P1 and P1, so I was just asking the two values that I see.
It's a typo. P1, P2, and P3.
Sorry, could you just remind me how do you get the 0? The D in this case.
Did you write down the definition for 0?
Yes, so hold on, let me go back to my notes. Wait, I'm not sure what to do. I don't see it. All right, I'll just have to go back in the video. Just a minute if I miss it.
All right, so finally, as I said, once you have these, you're now going to apply nodal analysis, similar to what we just did. Yep. Bearing in mind, of course, that Vs would be here. And what you want is an expression with Vs and Vr, and then you take it from there. All right, so it is now 2:30, 2:29. 2:29. I'll open the board again for those who will be attending the tutorial at 3 o'clock. Okay, so that's it from me. You're going to do the nodal analysis and verify that the answer is correct. But then again, since you'll be working through the next half an hour, let us restart at 3:15, all right?
Oh, sorry, can I go back one second on the question, sorry, sorry about that. All right, sir. Thanks, sir. That's it.